Welcome! In this video I'll introduce flux coordinates, which are a special kind of coordinate system in which the magnetic field is straight and often aligned to one of the coordinate directions, so one of the tangent vectors. These are widely used in tokamak physics because we have complicated magnetic fields which are curves, and so by aligning the fields, by aligning the coordinate system to the fields, we can make some of our life simpler. And if this follows on from a previous video on non-orthogonal coordinates, where we had a screw pinch, which is a cylinder like this, where we have a field line just going around like this. So it's a helical field line which is wrapped around the cylinder, and so we have a radial coordinate r, we have an angle coordinate theta, and we have a z coordinate going down here. And so we defined a field line coordinate system by finding two quantities which were orthogonal, which were constant along B. So defined a length L to be the distance along this field line, which is just B over BZ times Z. And then the two things which are changing, so L is changing as we move along the field line, but we want to keep two other coordinates fixed. So R is constant along field lines, and then we defined a poloidal angle eta, because as we move along a field line, this theta angle is changing because the field line is wrapping around here, and so we define a new poloidal angle, which is the cylindrical poloidal angle minus the distance that the field line moves. And this is r, the minor radius, times length. So as a field line moves distance L along the field, it moves this distance, this angle in theta. And so these two are both constant along the field. And using this, we found that the tangent vector EL is the unit vector along the magnetic field. So it was the B field divided by its magnitude. So it's a unit vector. And this simplifies derivatives, so for example B dot grad just becomes B field strength times d by dl. So it simplifies things like parallel derivatives. So we have two coordinates r and eta which are constant along the magnetic field, and this means that B dot grad r is 0, and B dot grad eta is 0. This just means that the gradient along the magnetic field of the radius or this poloidal angle eta are both 0 because they're not changing. And so that therefore means that the B must be proportional to the cross product of these two. So it's grad r cross grad eta. And we work out what this is using our coordinate system. And this turns out to be, so grad r cross grad eta is B field divided by BZ times R. If you work through from the previous lecture, you can work out what this is. We can use this to define a slightly different radial coordinate system, so we can essentially absorb this RBZ. So we write down that R times BZ grad R cross grad eta would be equal to B. And then this part here we can write as the gradient of psi, where psi is a flux. So psi is just BZ. So if you write this quantity psi as R squared, then we can write this magnetic field as B is just grad psi cross grad eta. And this is the Klebsch form of the magnetic field. So Kleb. So you have two functions, psi and eta, which are constant along the magnetic field, and then by taking the cross product you get a vector along B. So effectively it's two surfaces of constant, one of constant psi, one of constant eta, and where they intersect, that's the magnetic field. So where both are constant along a line. And so this is, you can write any magnetic field in this form. It implies you have a vector potential A, which is just eta grad psi, or psi times grad eta. So you can write down, okay, so any vector field which has zero divergence, so a solenoidal field, can be written in this form. But it's useful to think about what this psi is. So right here, so psi is a flux, which means it's a magnetic field times an area, and in particular it's the flux through, if we draw again the radius r, the flux psi is essentially this area times the magnetic field, and then per radian, so it's divided by 2 pi. So it's the field Bz, so Z is down to the page here. So Bz is in this direction. So the flux through this surface here is Bz times pi r squared, and then divided by 2 pi to get Bz r squared over 2. So this is the flux per radian. And we'll see that this extends to tokamaks or more complicated geometries, and the flux is a commonly used quantity in defining flux coordinates. So now we can see how this extends to tori, to tokamaks, for example. So the magnetic field lies on surfaces which are surfaces of constant psi. So we have magnetic field spiraling around this surface here, and on that surface psi is constant. They also lie on surfaces of constant eta as well, so, and also constant eta. But psi is usually the one that concerns us most, because these are the nested surfaces inside a tokamak. And so when you go into a torus, so you can define two kinds of fluxes here, because you have magnetic fields which are going around the torus like this. So you can define a flux surface based on toroidal field. So I draw this in as the field is going around like this. So this is B phi, it's the toroidal field. And so we could define surfaces as surfaces of constant flux. So define actually surfaces like this. So in the same way as it did for the cylinder, we just bent the cylinder around in a circle, and these are this is the toroidal flux. So the other way is to consider the poloidal field. So if you have a poloidal field going around the torus this way, this is B theta, for example, the poloidal field. We can take a slice through the torus, which is going around the machine like the toroidal field, but is a constant poloidal angle, so you get a slice like this, which then goes around the machine. So it's a ribbon which goes around the machine like this, so it cuts across like this. And this surface here is now cutting through the poloidal field, so it's aligned in the toroidal direction, so it doesn't have any, there's no toroidal field crossing it, but the poloidal field is going through this surface. So the poloidal field comes around here and cuts through this surface here. And this is the poloidal flux, psi p, or just called psi, because it's widely used. It's probably the most common convention, is that surfaces in a tokamak are defined by the poloidal flux, but you will occasionally see toroidal flux used as well, particularly in accelerators and other applications. Okay, so we've chosen the radial coordinates, often say toroidal flux, poloidal flux. There are some cases like Hamada coordinates where the volume of the flux surface is used as well. So the volume inside this surface is a radial coordinate as well. But poloidal flux is the most common. So having got a radial coordinate, we now need a poloidal coordinate. And there are many different conventions. In a cylinder, the poloidal coordinate is quite a well-defined quantity, just the geometric angle. In a torus, there are many possible choices of poloidal angle. So for the discussion here, it doesn't particularly matter which poloidal angle you choose. It does affect some properties of the coordinate system at the end. But for this discussion, I'll just show you what kind of poloidal angles people use, and then particular choices will have different coordinate systems. So I draw some flux surfaces, which are surfaces of constant psi. So these are surfaces that the magnetic field is lying on. I have some flux surfaces like this, and remember that in general they're shifted outwards by the Shafarov shift. So the axis of the machine is over the left-hand side. The simplest one is just to choose geometric angle. So we just have straight lines in theta. So another choice, we might want to have the poloidal angle and the radial direction orthogonal. You see in this case over here, if you have geometric angle, the flux surfaces and the radial coordinate are not aligned, are not orthogonal. So here we have some angles. If we want the radial direction and the poloidal angle to be orthogonal, then we can do that. And that simplifies some of the coordinate systems. So with an angle, the radial coordinate lines tend to bend outwards. So with a coordinate system like this, where now the radial coordinate is not straight, but is now orthogonal to the surfaces. So a final choice we might make is if we want to have constant distance along field lines between poloidal points. So we might have a constant arc length. So again, we can draw this in here. And now instead of bending outwards, these tend to bend away from the axis here. With a coordinate system, it's more like this. Because the field lines are wrapping around quicker on the inside, so there's a higher toroidal magnetic field on this side than there is on the outside, and so for the same poloidal distance, the points will travel further on the inside than they would on the outside, and so you end up with the coordinate lines kind of bunched together on the inboard side like this, and this will be a constant arc length. So each of these have some advantages in different cases, and so you'll come across all possible combinations of these. Okay, having chosen a set of flux surfaces, so a radial coordinate psi and a poloidal angle, which we'll call theta. This is our theta angle going around out here. Now we want to look at what the magnetic field looks like. So how do we align a coordinate system with a magnetic field? So if you take a single flux surface, so we say psi equals constant. So we'll plot what the magnetic field looks like on a flux surface. And now I've taken a toroidal flux surface and unrolled it in 2 dimensions. So here we have the toroidal angle, and here we have the poloidal angle theta. And in general, the field line is not straight on this line. So a field line might have regions where it's wobbling up, and might wobble around like this. So this is the B field. So B field is along here. Now, after a single turn in the poloidal direction, so after a field line has gone from 0 to 2 pi in the toroidal direction, it will have gone a certain distance in the toroidal direction. And in a tokamak, we often use a convention that this is q times 2 pi. So it's gone q times round the torus for every 1 time round poloidally. And generally q is bigger than 1. And then after, say, a single toroidal turn, so if you've gone, say, 2 pi over here, on average, it will have gone iota in the poloidal direction. So iota is called the rotational transform. So it's more often used in stellarator physics, where this is the average poloidal angle that the field line moves after 1 toroidal turn. In tokamaks, it's more common to use the q, because q is a flux surface quantity, so it doesn't depend on where you start or finish. You just once you go around the torus once poloidally, you've moved q times toroidally, and q can be integer, or it can be a irrational number or a rational number. and Q is called the safety factor. And it's called safety factor because there's a lower limit to Q. So if Q is less than 1, then the plasma tends to become unstable. If Q is less than 2, then there's a softer limit on the stability, and so typically Q should be high in order to avoid large instabilities in the plasma. And so it's associated with increased Q is associated with greater safety in that sense for the plasma, and so it's called the safety factor. One way of calculating Q is to integrate the gradient of this. So if you want to integrate along theta, for example, we want to integrate from 0 to pi in theta. We can find out how far we go in phi by integrating d phi, effectively. So we want to know that d phi is something times d theta, because then we can integrate in theta and calculate the change in phi. So we can calculate the change in phi and the change in theta by thinking about what the gradient of phi and the gradient of theta are along this line. So you have that b dot grad theta, for example, is magnetic field strength times d theta by dl, where L is the distance along the field line. And so the same way, b dot grad phi is just b times again d phi by dl, or again L is distance along the field line. And so you can work out the change in phi and change in theta along the field line by just taking the ratio of these two. And so we have that along the field line, so we have that d phi by d theta is just given by, you can see that along this magnetic field curve, the toroidal angle is a one-to-one mapping with the poloidal angle theta, so it's just a single function, so phi is just a single function of theta, and so you can just integrate this equation here to calculate the change in phi as you move a distance in theta. And this is often called nu. It's a function of psi and theta, and it's called the local pitch. It depends on the pitch of the field line, so it's how much toroidal field is there compared to poloidal field, for example. And then we can work out Q. So Q is the number of times we've gone around the torus, so it's the change in phi divided by 2 pi. So it's 1 over 2 pi times the change in this. So it's d phi from theta is 0 to theta is 2 pi. And that we can just write as 1 over 2 pi times the integral of this field line pitch. And so now we can use this field line pitch, the safety factor, to calculate how we would align a coordinate system with the magnetic field. So I'm going to go back to this picture of what the magnetic field looks like. We want a coordinate which tracks along this B field, and that means that the other two coordinates should be constant. So we have one coordinate which varies along this field line, and the other coordinates are constant as you move along the field line. And we can do this in two different ways. So the first way is we redefine the poloidal angle. So we consider how far the field line moves in poloidal angle as you change in theta, so as you change in toroidal angle. And so using this we can work out, we can define a new poloidal angle, which is the original poloidal angle minus basically the change in poloidal angle as we change in toroidal angle. And so this is if we moved a distance in toroidal angle, this is how much the poloidal angle would change. And so all we've done here is we've just taken this curve, and so as we move along the field line, we're moving in toroidal angle, and as we move along the field line, we move in toroidal angle, and so as we move along the field line, we move in toroidal angle. And so as we move along the field line, we move in toroidal angle, and so as we move along the field line, we move in toroidal angle. And so as we move along the field line, we move in toroidal angle. but we're also moving in poloidal angle, and this change here, this is this integral, and so now we're just subtracting the integral to find a quantity which is constant along the field lines. And so eta is now constant along the magnetic field. If for example this field line pitch, this is 1 over the field line pitch. If this is constant, then we can simplify this. So here we end up with a poloidal angle, which is shifted, but it depends on 1 over the safety factor q. And in this case, what we've got is a coordinate system where e phi is aligned to B. So I try and draw this in a torus. So I have E phi, which is along the toroidal direction. You have E eta, which is poloidal. And we have radial coordinate as well. So the whole coordinate system ends up being psi, eta, and phi. And phi is aligned to the magnetic field. The alternative way of doing it, and so now we redefine a new toroidal angle, so zeta for example, which is the original toroidal angle, and now we're just subtracting off the change in toroidal angle along the field line. So here we're going from some initial poloidal angle to a new poloidal angle, and it's the change in toroidal angle, so it's b dot grad phi over b dot grad theta. Now we're integrating along theta. And now this has a slightly different effect. So now we're aligning the field with the theta direction instead of aligning it with the phi direction. So here this again is the field line pitch, which again depends on psi and theta. And if this is constant, then the whole thing can be simplified. And you just get that the new toroidal angle zeta is just phi minus q times the poloidal angle theta. And now we've got a different coordinate system. So theta is now aligned to the magnetic field, and zeta is in the toroidal direction. So E zeta is in toroidal angle, and we have a radial coordinate as well. So there are some advantages to this coordinate system. For example, we still have a coordinate system in the symmetry direction, so that has some advantages for computational efficiency that we can take for our transforms and things in this direction. But the disadvantage is that this coordinate system is quite non-orthogonal. See, the parallel and the toroidal directions are quite close to each other because the toroidal field is typically quite strong. And here, as Q gets larger and larger towards the edge of the plasma, so in extreme cases at the x point, Q goes to infinity, this obviously has problems, whereas the alternative derived here is somewhat better in that sense, because as Q gets larger, the system becomes more orthogonal, and so this singularity no longer occurs. But now we don't no longer have a coordinate in the toroidal direction, just one in the poloidal angle. So both of these are used for different reasons. This second one is often used in flux tube codes, for example, in turbulence simulations.